Section 6.1 and 6.2, composite and inverse functions. What this means is, given two functions f and g, the composite function denoted by f composed with g, or that's how we would read it anyway, f composed with g, that's what that little circle there means. It means composed, is defined by f composed with g of x is f of g of x. The domain of f composed with g of x is a set of all numbers x in the domain of g such that g of x is in the domain of f. Well, what does some of that all mean exactly? So when we take a value, whatever x is, and we put it into a function like g, there's going to be an input, that's our x, and then what we get out after we follow whatever set of directions might be over here, whatever we get out is called g of x. We take that and put it into, so whatever comes out, we take that and put it into the function f, and that would be what this notation means, f composed with g of x. So how does that actually look in practice? I should back up a minute here. The domain the easiest way to try to describe how we figure out the domain is through an example. So I'll explain that in just a little bit. But so in practice, here's how this works. Let's take this first one, f of g of 1. This could be also written as f composed with g of 1. And the way that works, f of g of 1, is we're going to take the number 1 and we're going to put it into the function g. So we're going to take 1 and put it into this function and follow this set of directions. So whatever we put into g says to take that and multiply by 3. When we take that and multiply by 3, we're going to get out 3. After we've done that part, we take what we get out and put it into the function f. So when we put it into here, we follow this set of rules. We're going to take what we got out, we're going to cube it, multiply by 2, and add 1. When we do that, 2 cubed is 9, 27. 27 times 2 is 54. Plus 1, we're going to get out 55. All said and done. When we take f composed with f of 2, we work from right to left, so we take the 2, we put that into f, that would be this part right here, and then what we get out of that, we're going to take it and put it back into f a second time. That's what those two things mean. So we start, in this notation, we kind of start right, put it into here, then put it into here, and in this notation here, we start from the inside and work our way out. But what this means, we take this 2, we put it into the function f, which is right here, so we're going to follow these rules. We take the 2, when we put it in, we cube it, multiply it by 2, add 1. When we do that, we'd get 2, 4, 8 times 2 is 16 plus 1, we're going to get 17. That's out of this part right here. Then we take that 17 and we're going to put it back into f again, so we're going to cube it, multiply it by 2, add 1, and when we do that, we're going to get 9,827. Now, keep in mind, the numbers have to be fairly nice because we don't want you to spend too much time with arithmetic on the test. But if you had to do 17 cubed, I mean, you could do it longhand off to the side. Then, this last one, g of negative 1. One way of writing that could be g composed with g of negative 1. But what that means is we take the negative 1, we put it into the set of directions for g. So whatever we put in, we're going to multiply it by 3 and get out -3. That's from this part right here. Once we get that out, we put it back into G, and when we put it back into G, it says take it times the 3, so we end up with -9, all said and done. And that's kind of how this notation works. So then let's take a look at this mess here. We have f of x. This function, when we put something in, the set of directions is telling us to square it, multiply by 2, plus 5 times what we put in, plus 7. The function g of x is telling what we put in, to take it, times 2, and then add 4. So here it says find f of g of x. Find f of g of x. So f of g of x. This means, here we don't have numbers, but it's saying take g of x. So we're going to put something into x. When we get that something out, we get it out after we followed the set of directions for g. So we would get out of here 2x plus 4. We're going to take that, what we get out, and put it into the set of directions for f. When we put it into the set of directions for f, we're told to square it, multiply by 2, then add 5 times what's getting put in, so 2x plus 4, and then plus 7. Now I know you see x's in lots of places here, but when you look at this part up here, instead of thinking of them as x's, for me it really helps to think of them as the set of directions for what to do. So then when I do this, I would want to try to simplify this sum. I have 2 times, when I square this, I'd have 4x squared plus 16x plus 16. If you have to do some more work off to the side, you always can. 10x plus 20 plus 7. Do a little more simplification. We get 8x squared plus 32x plus 32 plus 10x plus 27. Combine like terms, 8x squared plus 42x plus looks like 59. So 8x squared plus 42x plus 59 is what we would get there. Now for their domain, so when we look at the domain here, we would want to look at the domain and figure it out from right after we put them together. So right after we put them together, do you see any sort of restrictions, any fractions with x in the bottom, or any square roots? No. So then the domain is just the set of all x's. Well, it's just the set of all real numbers is what it is, because there's no restrictions. Okay, so then g of f of x means to take x, put it into the function f. When we put it into the function f, we're going to put it into this set of directions and get this out. So we would get out 2x squared plus 5x plus 7. We're going to take that and put it into the function g, follow the set of directions for the function g. So when we take our input here, the 2x squared plus 5x plus 7, we follow this set of directions, so we're going to multiply it by 2 and then add 4. If I do some simplification, get rid of those parentheses, we'd have 4x squared plus 10x plus 14 plus 4. Combine the like terms, 4x squared plus 10x plus 18 would be the second one. Again, for the domain, when we find the domains, we want to look at right after they're put together. Right after they're put together, are there any restrictions? Any x's in bottom of fractions, or any square roots or fourth roots or something like that? No. So the domain is all real numbers. How about this one? We have For the function f of x, the set of directions tells us whatever we put in to do it plus 1 under 3. For g of x, the directions tell us for whatever we put in here, we're going to subtract 4 and then do 11 over that. So when we find f of g of x, we are putting x into the set of directions for g. When we do that, we take it, subtract 4 under 11. That would be this part right there. Then we're going to take that and put it into f. So when we put it into f, what we're putting in here is the 11 over the x minus 4. We put it into f, and when we put it into f, it tells us, the set of directions tell us to add 1 to it, and then it's all going to go under 3. Now, this is right after it was put together. So if I skip ahead here, for the domain, I look for the domain right after they are put together. And I think there's going to be some restrictions here because I see some fractions and I don't want 0 in the bottom. If I look at this small fraction, I don't want this small fraction to have 0 in the bottom. So what I don't want to happen, if I do my notes below this, I don't want x minus 4 to be 0 for the domain. And when I look at this big fraction, I don't want the bottom of the big fraction to be 0, so I don't want the 11 over the x minus 4 plus 1 to be 0. In this top case, x just can't equal 4, and in this bottom case, 11 over x minus 4 can't equal negative 1. I would multiply both sides by x minus 4, so I'd get 11 equals, or can't equal, negative times x minus 4. Do some simplification here. So subtract 4, multiply by negative 1. X, or negative 7, cannot equal x. So my two restrictions come from the fractions. The domain is going to be the set of all numbers, or set of all x's, such that the two restrictions, x cannot equal, let's see, can't equal 4, can't equal negative 7. So can't equal 4, can't equal negative 7. And that domain comes from looking at the function, the composition, right after it is put together. Now here, I would still want to simplify this. In order to simplify this, I want it just to be one fraction all said and done. So what I'm going to do, to make this little fraction go away, I'd have to multiply by x minus 4. If I do that to the bottom of the big fraction, I got to do it to the top of the big fraction. So on the top, I'd have 3 times x minus 4. In the bottom, I would take this times both pieces. So it's going to be 11 over x minus 4 times x minus 4 and plus 1 times x minus 4. In the top, we'd have 3 times x minus 4, and in the bottom, those are going to cancel out, so we'd have 11 plus 1 times this is plus x, and then minus 4, so 3 parentheses x minus 4 on top, and the bottom we have x plus 7, like that. So there would be it simplified. This is in factored form in the top. A one-to-one function. A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are two different inputs of a function f, then f is one-to-one if f of x1 does not equal x2. So what that's saying is, no matter what two numbers we put in, no matter what two different numbers we put in, we're always going to get two different outputs. This right here, this example, this is one-to-one. No matter what two things we put into it, they're never going to the same place. The second one is not one-to-one because we have two different inputs that are going to the same place. An example of a function that's not one-to-one, so if f of x is equal x squared, this is not one-to-one because I can put in a -1, and if I put in a -1, I get out 1. I put in a different number, I put in a +1, and when I put in the +1, I still get 1 out. Two different numbers going to the same place, not one-to-one. This last example is not even a function because we have one number that's getting split and going to two different places. So this last example, this would be like if two different people in the class both got, let's say, an 85%. So two people both get 85% as a final grade. This first person, this top person, I decide, you know what, they got an 85%. They're going to get a B. This bottom person, yeah, they got an 85%. They're going to get a C. How happy would those two people be? Not very happy. So if one same number corresponds to two different things, it's not going to be a function. Now, this example, this one right before it, let's say here, if I use that grade analogy, let's say somebody gets a 83%, somebody else gets an 87%. They are both going to get B's in the class, whether they got an 83 or an 87%. Two different numbers going to the same place, it still is a function, but if the same number tries to go to two different places, not a function. However, keep in mind, this right here, this is not one-to-one. So if it's one-to-one for every single percentage, there would have to be a letter grade associated with it. So our grading scale is not a one-to-one function. What we can do to test graphs of functions to see if they are one-to-one is with a horizontal line test. If every horizontal line intersects the graph of a function in at most one point, then it's one-to-one. So this one right here, no matter what horizontal line we put on here, it's only intersecting the graph at one spot. So it's one-to-one. This one is one-to-one. However, let's say we took a different graph like this, y equals x squared minus 5. Here, if I put a horizontal line on there, it's intersecting, that same horizontal line is intersecting at more than one spot. This is not one-to-one. So we're putting in two different x values, but getting out the same height or the same y value, not one-to-one. Then we get to what an inverse function is. Suppose that f is a one-to-one function, then corresponding to each x in the domain, there's exactly one y in the range, because f is a function, and corresponding to each y in the range of f, there is exactly one x in the domain, because f is one-to-one. The correspondence from the range of f back to the domain of f is called the inverse function. The symbol f inverse is used to denote the inverse function. Well, what exactly does that mean? Like, how is that working? When I think of inverse, an inverse is what undoes. So if I paint a house, the inverse would be scraping the paint off. It's undoing it. If I drive into the garage, the inverse would be backing out. So inverse undoes. In words, what this means, suppose that f is a one-to-one function. So the input 5 corresponds to the output 10. If we put 5 in, we're going to get 10 out. Put 5 in, get 10 out. This would be like you put 5 $1 bills into a machine and you get out 10 50-cent pieces, or $half. Well, if then we wanted to undo that, because we don't like 50-cent pieces, they're heavy in our pockets, if we go to a different machine that's right next to it, the inverse machine, when we would put those 10 50-cent pieces in, we're going to get out 5 $1 bills. So if a function has an input of 5 corresponding to an output of 10, the inverse function is going to have an input of 10 and an output of 5. It undoes what originally happened. Some more examples of inverse functions. So if we look at these states, Indiana, Washington, South Dakota, North Carolina, Oklahoma, and we look at their populations, notice how each of these states has a different population. So if we wanted to draw a function or lines between the states and the populations, each state is going to correspond to exactly one unique population. The inverse would say, can you cover up, or can you instead take the population? Can you look at the population of those and determine what state it is? If we can look at the population, determine what state it is, that would be the inverse. It would be like the original function. Somebody tells you, hey, Indiana has 6.5 million people. And then you turn around and say to somebody else, hey, this state has 6.5 million people. Do you know what state it is? And they say Indiana. That would be like the inverse. If a function f is a set of ordered pairs, then the inverse function denoted, excuse me, it's like, there, now that typo's fixed. So if a function f is a set of ordered pairs x, y, then the inverse function denoted f inverse, that's what this little -1 means there, is the set of ordered pairs x, y, or yx, I should say. So if we have an input of x and we get out a y, in the inverse, when we put in the y, we're going to get out the x. So for an example, find the inverse of the following one-to-one function. So we have the original function. What the original function is doing, it's taking -2 to 5. So then in the inverse, what that's going to be doing is undoing it. So the inverse is going to take 5 to -2. The original function takes -1 to 3. The inverse function takes 3 to -1. The original function takes 0 to 4. The inverse is going to take 4 to 0. The original function takes 1 to 1. The inverse function is going to take 1 and bring it back to 1. The domain of the original, what's going in? We have -2, -1, 0, and 1. There we have the domain. The range, what's coming out? 5, 3, 4, and 1. 5, 3, 4, and 1 is what's coming out. When I look at the inverse, the domain, what's going in? 5, 3, 4, and 1. 4 or 3, 4, and 1, which if you notice is the range of the original function, and that's good because the inverse is supposed to undo. And the range here, the range, what we get out should be the domain here, And if we look, -2, -1, 0, 1, 2. The range is the domain. So that's good. Verifying inverse functions. If two functions are inverses, when we put one inside the other, or the first inside the second, or second inside the first, we should get back to where things started at. So f inverse of f of x is equal to x, where x is the domain, and f of f. This is what this is saying. If we put them inside each other and get back to x in both cases, then they are inverse. So when it says verify f and g are inverses of each other by showing that f of g of x is equal to x, well, what this is saying, f of g of x, when we put g of x, so when we put something into g, get out this, we're then going to take that, what came out, and put it into the function f. When we put it into the function f, the -1/2 times x minus 3, we're going to multiply it by -2. So we're going to take that, multiply by -2, and then the 3 is out front. When we do that and do some simplification, we'd have 3 distributing this minus, or multiplying -2 times -1/2. That's going to be +1 times x minus 3. So we get 3 plus x minus 3, which is just x. So when I put g of x into f, I get back to x. If I take an x, put it into g, what I get out, put it into f, it gets right back to g, or right back to x. If I put f of x into g, so if we put f of x into the function g, we'd be taking what we get out of f, so we'd be taking the 3 minus the 2x, what we get out of f, putting it into g, so we take this 3 minus 2x, we put it into the set of directions, which tell us to subtract 3, and then multiply by -1/2. When I do that, we'd have -1/2 times -2x, the 3 minus 3 goes away, and -1/2 times -x is x. Because both of these directions, or both of, depending what we did first, ended up at x, these are inverses. Now state the values of x that need to be excluded from the domain of f and the domain of g. For the domain of f, if I look here, does anything have to be excluded? No, it's just all real numbers. When I look at the domain of g, here, g, does anything have to be excluded? No, all real numbers. Neither one of them have fractions with the variable in the bottom or denominator, and there's no roots. So nothing needs to be excluded from their domains. Some more practice with this. Verify that these are inverses of each other by showing that when we put g of x into f, we get back to x. So if I take something, put it into g, I would get out this right here. So for f of g of x, when I put something into g and follow this directions, I get out the 3x plus 5 over 1 minus 2x, and then put it into f. When I put it into f, I would have to follow this set of directions. So I take what is getting put in, 1 minus 2x, follow this set of directions, so subtract by 5, and then in the bottom we'd have 2 times what's going in, 3x plus 5 over 1 minus 2x plus 3. Looks like kind of a mess, but I want these little fractions to go away, so I'm going to multiply the top of the big fraction by 1 minus 2x, the bottom of the big fraction by 1 minus 2x. When I do that, I have to take this times both parts on the top and on the bottom. So on the top, I would have 3x plus 5 over 1 minus 2x times the 1 minus 2x, and then minus 5 times 1 minus 2x on the top. When I distribute on the bottom, we have 2 times the 3x plus 5 over 1 minus 2x times the 1 minus 2x, because I'm distributing this to both pieces. I'm multiplying top and bottom by the LCD, the least common denominator, is what I'm doing. And then distribute it to the 3, so we have plus 3 times 1 minus 2x. When I look at this, that goes away, this goes away. In the top, I'm left with 3x plus 5 minus, do the distribution, 5 plus 10x. And in the bottom, do the distribution, 2 times 3x is 6x plus 10. Do the distribution, plus 3 minus 6x. So in the top, 3x, those are going to go away. We have 13x, and in the bottom, these go away. Over 13 simplifies into x. So when I put something into G and get this out, put it into F, it undoes it, and I end back up at just x. Now, to make sure it's an inverse, I still have to do this part right here. So I have to take f of x, which is the x minus 5 over 2x plus 3, and put it into the function g. When I put that into the function g, I have to follow this set of rules here. So I'm going to do 3 times what's going in, x minus 5 over 2x plus 3, plus 5 over 1 minus 2 times what's going in, x minus 5 over 2x plus 3. To make this simplify, I'm going to multiply both the top and the bottom by the LCD, the 2x plus 3. And then I'm going to have to distribute it to both parts on both top and the bottom. So when I distribute it to the top, when I distribute it to this, it's going to cancel itself out. So I'm going to be left with 3 times x minus 5, doing some of this in my head. And then when I distribute it to this, the 5 times this is going to be plus 10x plus 15. When I distribute this to the 1 times that is going to be 2x plus 3. And then when I distribute here, we're going to have minus 2 times, that's going to cancel out, so just the x minus 5 is going to be left. Doing some simplification on top, we have 3x minus 15 plus 10x plus 15. And in the bottom, we have 2x plus 3 minus 2x minus 5. Well, what are we left with? In the top and the bottom, in the top we're left with 13x over the bottom. Let's see, this should be a plus 10 when I distribute that, so over 13, and we're left with x. So yes, they are inverses. Now, all that work, and what do we still have to think about? We still have to think about the values of x that need to be excluded from the domain of f and the domain of g. So what needs to be excluded from the domain of f? Well, what we can't have the 2x plus 3 be 0, in which case x cannot be negative 3 halves. What about the domain of g? For the domain of g, What we cannot have is we cannot have the 1 minus the 2x, this bottom, be 0. So we cannot have x be 1/2 when I do the solving for it. Here's a theorem for you. If the graph of a one-to-one function f and the graph of its inverse, well, not if, they are, the graph of a one-to-one function and the graph of its inverse function f inverse are symmetric with respect to the line y equals x. So if we graph a one-to-one function, and its inverse, they are going to be symmetric with the line y equals x. So, practicing, if we were to graph this, if we would want to graph the inverse of this function here, what we would want to do is first graph the line y equals x. So when I graph the line y equals x, that line would look something like that. The inverse, it's folded across this line. So the inverse, this point, would be over here because it's going to get folded across the line. This point, when it's folded, is going to be right on the line. This point, when it's folded over, is going to be here. And this point is going to be down here. So then I connect those points and I get the inverse of the graph. How to actually find the inverse of a function? If I wanted to go about figuring out what it is, to do that, we would interchange. So first instead of using the f of x, we use a y equals, and then we interchange the x and the y's. If possible, we solve for y in terms of x, and then check the result. So if we're going to find the inverse of this function, instead of using the f of x, if we use y, 3x plus 1, the inverse, this is the original, the inverse is going to be found by swapping the x and the y. So this here is the inverse. But usually we like things in terms of x, so we solve for the y. So we're going to subtract 1 from both sides, then divide by 3. So we get y is equal to x minus 1 over 3. But really this y was from swapping. So this right here is really the inverse. And so our inverse of x would be the function x minus 1 over 3. And then if we wanted to double check that, we would put this into here and this into there. But there would be our inverse. So, another example, we're told that this function f of x equals x cubed plus 2 is 1-to-1. Find its inverse. Well, to find its inverse, the original function would be the f of x, or y, equals x cubed plus 2. This is the original. Then, to find the inverse, we swap the x's and the y's. X equals y cubed plus 2. This is now our inverse. And we are going to solve for the x. So we would subtract 2 from both sides, get x minus 2 equals y to the third, and then cube root. So we have the cube root of x minus 2 is equal to y. But again, this y is really our inverse. So this cube root of x minus 2 is equal to the inverse function right there. Graph f inverse, and y equals x on the same coordinate axis. So if I were to do that, we have the line y equals x. This function here, the original, is x cubed plus 2. It's the x to the third function shifted up 2. So it would look something like this. And if we want to do the inverse then, so this is the original function, x to the third plus 2. The inverse is reflected over this line. So this point would be over here. This point would be over here. This point over here. This point would be over here. This point would be over here. This point would be right on. So what that's going to do, it's going to look something like this here. Would be the inverse. And again, this right here would be the inverse. Now that my pen has a new battery, it's writing a lot better. Some more practice. We're told that f of x is equal to x over 4x plus 1 is 1 to 1. Find the inverse function. So the original is y equals, how about I do this in black? So the original is y equals x over 4x plus 1. That's the original. To find the inverse, I swap the x's and the y's. 4y plus 1. I'm going to try to solve for y. So I want to get this out of the bottom. I'm going to multiply both sides by the 4y plus 1. So I get x times 4y plus 1 is equal to y over 4y plus 1 times 4y plus 1. What that does, makes that go away. And then if I distribute this, I get 4xy plus x equals to y. I want to get the y's onto the same side, so I would subtract 4xy. I get x is equal to y minus 4xy. I see y's there. I'm going to factor them out. So y times 1 minus 1. Kind of try to clean this up a little bit. Here. So 1 minus 4x. To get the y by itself, I would divide by 1 minus 4x. So my y, which is really y is equal to x over 1 minus 4x, but this y is really the inverse. So my inverse function, and how about I write the inverse function in red now that I finally found it. The inverse function is x over 1 minus 4x. And keep in mind, when you see these x's here, these really are just a set of directions for what to do. So they don't represent the same x that's over here. It's just a set of directions for what to do. Now find its inverse function. We have the inverse function there. Find the domain and range of f. So for the original function, the domain, when I look at this function for the domain, the only thing that we have to worry about is the bottom, the 4x plus 1, can't be 0. When we solve that, we find out that x can't be equal to negative 1/4. So for the domain, it's the set of all x's such that x cannot equal negative 1/4. So it cannot equal a negative 1/4. The range, if I think about what's going on graphically here, this function the x over 4x plus 1. It's got the 1/4, so it's got a horizontal asymptote at 1/4. It has a vertical asymptote at -1/4. And so what's happening here, if I put in, let's say -2, we'd have negative over negative, so positive. This graph is looking something like this. The range, the only thing that it can't hit is that horizontal asymptote. So the range is a set of all y's such that y is not 1/4. Then let's take a look now at the inverse. For the inverse function, the f inverse of x over 1 minus 4x, that is the inverse, not of. So the inverse function equals, that should be an equals there too. The inverse function is equal to x over 1 minus 4x. For the domain, it's everything except where the 1 minus the 4x is equal to 0. So 1 minus 4x can't be 0. If we solve what we're going to find, the x can be anything except x cannot equal, when we solve this, it's going to come out to can't equal 1/4. Which, take a look here, the domain can't equal 1/4 is of the inverse. The range to get back can't be the 1/4. For the range, when I think about what's happening with this function, there is a horizontal asymptote at -1/4 when I look at the number in front of the x's. So there's a horizontal asymptote at -1/4, which is where it's not going to be able to hit. So the range is everything, all the y's, such that the y cannot equal -1/4, which matches with this domain right there. And that's good, because inverses undo the original, so the domain and the ranges flop. Well, I think that does it for this particular section. Good luck, and let me know if you have questions.